last time we were left with discussing the Picard group and the Jacobians. So I'll recall that first. We have about like half an hour material to finish up. So F if X a covers right over S. So I thought about how to define Picard streams. Maybe do it this way. So let's make two assumptions. First of all, well, let's say my pi x OS has to F lower square OX is 9. So this is basically equivalent to all geometric fibers. Okay, all fibers are geometric. Secondly, I want to assume that S section. So we call it a sigma. Okay. Under these two assumptions, I want to define function from maybe I want to be flat. Let's say n is not here. Flat finite time schemes over S of sense. Last time I defined it a little bit, it's already complicated, but it's equivalent to the following definition. So let's first of all give the more it's a more explicit definition. So L is a line bundle of X from S such that if you pull back to L along the section here, this is OS. Okay? In the sense that you should think through some sort of curve. And of course there's kind of a section here. You want your line bundles to be trivial on one of the sections. Another way to think of this is that S is the line, all line, let's say just make it this way, line bundles T. But then you portion out the equivalence relations that L is equivalent to L prime if L is isomorphic to L prime. Pi alpha star and K, where K is a line bundle. And you can it's not that difficult to show these two are equivalent in the sense that in each of the equivalent class, I can just write it down like this. So suppose I have a line bundle. Of course, you have a map going this way. On the other hand, if you have a line bundle here, you can make this line bundle to be trivial on a section by basically cancelling with the pullback of. So you first of all look at the line bundle and see what it looks like on the section, and that will be first, and then that will give you a line bundle here, and you switch back upward up there to the line bundle by the inverse of that line bundle. Then your residual line bundle to this inverse section will be and this is precisely what the equivalent class is. in this particular equivalent class, there's a unique line bundle that's trivial along this section. Okay? And the upshot of this is PXS. Add a little bit of things. I need a 0 here. This is a alignment on this list. Degree 0 on each fiber. If I put the 0 here, that means that this is degree 0 on each fiber. Then this Picard relative to 0 is represented by and the millisecond. I think the radius of that. Let's call it K. Or S. Oh, I wrote but then I want to remark that we talked about the situation over compact numbers. In that case, pick 0 is the same thing as Jacobian. But I guess for skips, defining Jacobian is not that easy a task. So instead, we use 0 as so now, let's move on to the technology. So again, now I want to have my sorry. I apologize. If okay, proper smooth. Okay. If x to f is proper smooth, then this is represented by a Milli scheme. The reference I had required the first I have to say that number. So, proper smooth curve from G to G, that's okay. So that's what we're going to consider anyway. So let's see, now x is the proper smooth curve of G to G. So then I can consider so this construction will give me a pick x0, and I can take the tape module of that. That's to say, we start with over here. So then I can take that. That's what this neighbor's limit. Partial algebra. And I'll take 0. So L to the n portion point. And then I take the actual points. I mean, roughly speaking, this looks like ZL. Oh, sorry. After taking limit, this looks like ZL to be twice of the limit. And this one carries, because we're taking fractional points, this one carries the action of the Galois group Q. So that gives us a 2D dimensional version. If I burn out, given that it will give us a 2D dimensional representation. also let me mention that becomes OD by BL, which is the okay. So fact we discussed last time that the BL compared to the ethyl chromolysis setup. With QR condition, the optimized cyclotron little. We give an explanation of this last time. Let me say that this is let me give a lemma. If curve X has good reduction at P, then through replication we obtain is unreplicated. And there's another statement of this lemma which I'm going to prove. Oh, it's stated. You know what? So actually, when we actually associate Galois rotations, we're going to take this thing. So I should be thinking of BL of this abelian variety tensor with the inverse of the constant. So later, we'll consider BL of this thing tensor with the inverse of the constant. But that's just a twist. It's not just that. It's a question of normalization picture. Oh yeah. Which on this side of Q. We tend to Q bar. Okay. But it's I'll show the lemma in a bit in a sort of more explicit way, but I want to mention some more facts. The previous eigenvalue would be on BL. Are repeatedly negative half weight numbers. And are well. And also now BL say X. Zero. 1. Well, now let me give through a not quite a proof, but through an illustration of. I guess I want to give you an explanation of why this is unreplicated. Aside from the reduction, I want to see this from see it geometrically. So the meaning of x having good reduction to t is that I have an x over spec. Delocalize it. It's proper space such that the degenerate fiber is fine. X. And from this, I can get a because 0 x over dp is over spec. Right, this is a Beaton scheme like so. And I want to say that sorry. So here's the fact that multiplication by L is total A tau. Okay. Or rather, you can replace this by kind of iramified and flat. So I just want to say that multiplication by L is a very nice operator on this part. That's a bit bright relative to dp. Now, I can look at the following. If I look at certain Q bar point on the card, because I said the video bright is proper over spec Q. Therefore, the integral point is the same thing as rational point. For any sort of projective variety, proper variety, the Q, forget about the Q bar. This Q point is the same thing as D point. Because whenever you have a Q point of the projective variety, you can Q all the denominators by common factor. But once you have D point, you kind of take reduction model. Not quite keep rather the next modulo a prime over. So this math goes as how if you have some x1 xn explicitly, first of all rationally, and you can scale them. You can first of all scale them so that all these xi's are in dp bar, but not all. Let me just pick this dp bar. Not all in n. But not all of them in the max binary. Now you can plot x bar. Okay. Benefit of working with projective. Right, scale it, kill all the denominators. And also, whenever there are common factors in the numerator, you can also kill them as well. Perfect. Right. So like so now if I take sort of L points, this one. In some sense, so what's happening here is that on these sort of, I think of this sort of as spec dp, on the generic fiber, I have some repeat and right to destroy it. So this is Q fiber. This is MP fiber. Okay. So what I have is that the L torsion kernel of this one is like kind of a section like that. So it links some point on the generic fiber to a point on the special fiber. Therefore, or rather under this projection map, this will go to 0 of x. Okay. And because this map is well defined, the Galois group action over here must be compatible with the Galois group action over here. And this way, somehow you see explicitly that the Galois group action on this one, in particular the QP action, will be just exactly given by, I guess, sort of, it is somehow restricted to. One thing I have to be careful here. I apologize. So here's the problem. Let me do it for QP, and I explain what happens. Why the argument might work for QP. So let's do a QP version upstairs. Right then. So if I do a QP version, this will tell you that Galois group action on this space will be actually the same thing as Galois group action on this space. And therefore, the representation in P is unrefined. And now raise the question, why the same argument doesn't work if I replace QP by Q? Here's why. When I say, okay, I take reduction mod a maximum ideal, if I were working with Q, from Q up to Q bar, my P was split into many primes. I can only modulo one of the prime above. But I have a choice which prime I modulo by. That choice is not equivariant. It's not sort of canonical with respect to the Galois group QF. It is canonical after you fix a prime P and embed your Galois group QP. So I can use this argument for QP because I already kind of fixed one per prime in Q bar over P. And then I work with that Q bar with that contribution. And this Galois group action will be compatible with the choice of this prime P and modulo that prime P. And therefore, for that action, this Galois group will be compatible with the Galois group FP action. But if we were to argue this using Q, with the choice of which prime I choose, for different Galois group Q, I would somehow this map is not equivariant for the whole Galois group action, it's only equivariant for the action of the Galois group existing position. So all of us saying that replaced by Q, and we see that on the node that this Galois group action will actually factor through the Galois group by that Q, and therefore this time see it on the right. Any questions? Sure, this is not important. So because here when I modulo some prime, I choose prime opposite. So that choice of prime will not be stable under the Galois group action. Any questions? So let's talk about just say very briefly about fat reduction. This will be used in 2 lectures. So I just talk about it. There has to be vector O. O equation 3 and practical and a oh, yeah, you're right. I should have done I just right. I should have just done this. Yeah, so, yeah, right. So this set and this set at the same time. So then basically you got the point is there's no two sort of lines clashing to one. So there's no 2 points here. Yeah, so that's right. In terms of sets. Okay. In other words, how you can think of this is that finding scale to the n torsion points is just kind of solving some equation. And this equation has no multiplicity. How does it instead something like the Jacobi equation works? Therefore, there's no, all the roots are, so therefore, whatever the degree of the map. So let's say this is a proper. X is relative. With geometric connected fibers. Such that xk, GR fiber is smooth. Don't say one more thing. I have to assume that my x has a section. Should have assumed that earlier that my x is geometrically connected and then on the section I have a 2 point. So let's assume that. Otherwise the entire group definitely. Okay. So xk is smooth of genus GR fiber is smooth of genus G, but it's not the definite PR function does not need the 2. It's special fiber. Say I have a point. Point of this. Completion is either some sort of old time or so put the GR fiber of this guys. The special fiber, if you complete it, So it looks like either this one. So let's speckle K and have small k. So germ fiber is small special fiber. And germ fiber is kind of, but then the special fiber will look like this. And of course, if you kind of complete at the point over here, then the completion looks like distribution curve. O with one variable is one variable. But if you complete at this point here, so this will look like this. Instead, because you see that if you modulo this one, if you focus by var by k, S over O with k. Look at the special fiber of this one. This becomes k prime of Ts modulo. Now this becomes trivial of Ts. So locally it looks like two coordinate ranges. So what I'm saying is that only these two types of singularities appear on this equation. Suppose we're in this sort of nice equation, and this will be the situation we consider when we talk about module curves. And there's some nice so there will be some sort of crossing. In such a situation, I want to take a point on special fiber and then complete with respect to the whole right. Then, under this assumption, let's take the curve function I discussed earlier. It's represented by a flat connected group scheme. Regret that I'm using. Sorry, please allow me to change it to J. Because here we know for curve Jacobi is the same thing as the car. It's shorter. Okay. B is J. Because J is shorter. Such that first of all, on the generic fiber, this is going to be the variety. As we would expect, so you have a smooth curve, of course. Take the cut function, you get the right. Secondly, let's look at a sort of special fiber here. I have taken the tutor of the special fiber. Namely, I wanna basically, instead of taking the union of these, I take the disjoint union of these here, resolving all these singularities. So the correct way to say this is that I take the normalization. Of the special fiber. So basically what it does is basically take this as just disjoint union of these. And this would map to my x. Then we have I have the following exact sequence of group C torus goes to this. I want to understand Jacobian of special fiber. Well, sort of the same thing as the Jacobian of the whole thing, base change of K. So this so-called semi-amines. So this will be, because After I take normalization, each of the xi iota will be proper and smooth. So each one of these is proper smooth. and of course, if I have so if I have a line bundle on this sort of not quite nice space, I can pull it back to each of these here. So therefore, I get a natural map from the Jacobian of x k of the special fiber to Jacobian of each of those irreducible components, which themselves are smooth. So therefore, each of them is a beta variety. And this turns out to be surjective. And then the kernel is a torus in the bunch of GM. Right. So the middle guy is, we often call it a semi-abelian variety, or semi-abelian scheme. So this part is so-called abelian part of this. And this is sort of fork part of this. What we use is a very, very special case. Let me specify what we really need to use. What we will really use later on. So before that, let me say that similar to earlier, last time. If I have an h x to y is a finite flat prism of such relative curves, I will get the two factorial maps named after star of S. Both are over S. That schematic ring. I have basically I just want to have maps going both ways. I'll just get one special case. That my x over y. This is over the p. Okay. We know that all my setup, the GR fiber are power smooth for this curve. But I want to know what it looks like on a special fiber. The only case I'll be interested in is the case that this is power smooth. So this guy is power smooth. The particular special fiber is a projective smooth curve over F. X is not. So X looks like a union of two components. Typical picture we draw on a special fiber. So there are two components. They will meet at many points, not under one point. Many points. So the answer is 1. Well, we put y on. Okay. So therefore, I have H1 and I have H2. Two maps on the special fiber. And now I want to know what it looks like. What it looks like on the map on the special fiber. So what it looks like is following. So I have natural map from Jacobian of S down to Jacobian of Y. And I want to look at certain. structure theory of this Jacobian of this one inside. It looks like a ball. It looks like some sort of one goes first, goes to this S1 bar times S2 bar. Right. So that's the structure theory of the Jacobian of the upstairs term with that stuff. And now I want to understand this. How this map go? So let's sort of look at how the torus will go. One thing we know about torus, we don't have to know what it is, but I know something affine. On the other hand, this side, because I assume this y is proper smooth, so this is proper. Right? Yeah. So here's an algebraic geometry fact that if you have something affine mapping into something projection at the geometric sense. This has to map to a point. If you have something affine mapping to the projection from top of right, has to map to the front. Wait, go the other way. Oh, shoot. That. This is loop speed. That. Very sort of. I'll think about that and I'll write up. But there's no torus to be the right. There's no movement from torus to be the right. Maybe I will. I'll cut that part off. There. Now we know that this map will be from this one vector through these two parts and then going down to this. Sort of, like. Okay, I'll leave as this because we'll use this in 2 lectures when putting the ecological relations where I have to understand how the H lower star does on the spectral fiber. Any questions? Okay, now I want to. So go a little bit, go a little bit faster. I guess most of you have already known. Switch. So wonderful magnets. So for module forms, I need these level subgroups of SL2D. And gamma naught n mod gamma naught 1 is E mod n. This is very important. The relation between gamma 1 and gamma 0. upper half plane. It's acted on by x on z. And from this I can define some sort of quotient. By this action. Wonderful f of weight k. Of n. Different type of I. Finding all these terms is a holomorphic function. Such that first of all, f of ab plus b, cz plus d is chi of minus c. Okay. So the only maybe slightly down to think out because my gamma my ABC is in gamma n, C is divided by n. So therefore it will force D to be D2. So this will force D to be relative to garbage n. Because the determinant is 1, so you can't have C and D have common divisor. So therefore I can apply chi to this form. Secondly, I want it to be a cut form. I want to consider some sort of boundedness condition. I think the best was for each gamma being A, B, C, D in SL2Z. If I do CZ plus D minus K of FA plus D, CZ plus D is bounded. Essentially, as Z goes to each of the so-called cuts, boundary of this space, roughly speaking, the gamma n will look like something like this. Like it will be 90 very. Something like that. So there's 4 cuts in this picture. You have I infinity. The cut of infinity, and this cut here, cut here, cut here. Oh, actually, no. How is that? Probably quite anyways. So there's 4 cuts. You want your function f to be bounded going this way, and somehow bounded going this way. But then, say it's bounded going this way, it's best to turn this cut into I infinity. That's what this gamma does. Gamma will take a gamma that turn this point up to I infinity, and then say this is bounded. But when you turn it up, there's a factor CZ plus D to the minus K, because you want it to be compatible with your factor CZ plus D minus C. Okay. So let's continue the discussion. minus we found it, we require it. I require this expression to go to 0. Okay. Maybe let's also discuss a little bit of variance of this. So, for example, maybe I should say, so for example, if a chi is trivial, then I sometimes write sk gamma naught n for m, for sk of n trivial for m. Okay. Because in that case, this function is truly invariant under gamma naught n action, as opposed to having a character. Another variant of this is that I say f has level gamma 1n if somehow this relation holds for A, B, C, D gamma 1n. So in this case, so in this case, let me say that the quotient quotient gamma naught n over gamma 1n will act naturally on sk of gamma 1 for m. Where sk gamma 1n means all the forms satisfying this condition with this replaced by gamma 1n. Okay? So if I just consider all the forms with gamma 1n, this gamma naught n over gamma 1n will act on this space here. Let's make this action explicit. So for each E bar in this one, I can always pick A, B, C, D in gamma naught n such that D is congruent to E bar following. Then I can define it's called diamond E bar. It's called angle bracket. Actually, D is just CZ plus D minus K of F A plus E. And this is independent. This is independent of choice of things. Because a different choice will differ by something in gamma 1n, which leaves F there under this type of expression. And what's the relation between this gamma 1n form and this action versus our earlier discussion of level n limit typos character? It's the following. So then, when you have this action, sk of gamma 1n, under this action you can take some sort of eigenspace interpolation with respect to this diamond operator action. Not that diamond. Small diamond. So chi of sk. So our earlier definition of level n limit typos chi is nothing but taking the gamma 1 level and then taking this diamond operator action corresponding eigenspace. respect to different characters. Let me comment. So this, I asked people whether this diamond is big diamond who wrote the book. I think the answer I thought mostly is not. Just happened. A friend that happened to have the last name like. And right. I think it's called diamond of bread because I guess it's angle bracket is like a diamond. That's fine. I wrote it. But turned out this diamond of bread is very important in the theory of modularity. Turned out to be very useful. So that's why I particularly talk about this. So later on we talk about modularity lifting results. It's kind of interesting that how I can also exploit the relation between gamma naught of n and gamma 1 of n. So that's how it gets cuts. So yeah. Let's talk about Q expansion. So 1101 belongs to gamma 1 of n. It will tell you that at the taking n plus 1. And by Fourier analysis, and I assume everyone knows that, so just gloss over to get the Q thing. So that's F by F as FQ means alpha median. Where Q stands for E. So, practical break. So it is not by the level, so have a TP operator. Where S fixing the cast one. Right. So what it does on the function following is 1 over p of sum over these, and then you plus it's not clear at all from this expression why this will take a module form of level n to module form of level n. But I guess later on we'll see. As you learn it, type of theory of module form. If FQ have a Q expansion, and this expression will read as follows. So the first sum with the 1 over p here will give you this expression. And then it's a question of whether I want to say another sum. So let me put these together. And then A and Q and N. Just to make a remark, as I said earlier, so Q and N. I'm not going to put this back. You can refer to any standard books on what to divide n. We have a similarly defined operator. But also it's denoted, so let me denote it by UP. Some reference write P for operator for not dividing n and dividing n. But for number series, it's opposite. When P divides the level, right, use another letter U. The reason is because it looks different. The difference basically you lose the last term. So with the sum of A. Lose the last term. You don't have to. Mostly just recall basic facts about building blocks. Say that F is normalized eigenform. Normalized is A1 equals 1. And eigenform, I mean to say it's eigenform for all these fact operators. And for every the non-divide n, this PP is an eigenform. And by just looking at the expression here, it's an eigenform. If I want to know the eigenvalue, I just compare what A1 is. So the first in the Q expansion, what's A1 coordinate? So A1 of TP of F. So we look at the term where I get this exponent to be 1. This one has no hope to be 1. So A and n being 1, so then I see AP. AP of F. AP. So basically in the Q expansion of TP of F, the Q coefficient on Q precisely. So therefore, if you compare the infinite space compares coefficients. Just pick one. And then not divide it in the same way. And in addition, because of these recursive relations we have over here, we can deduce that np squared plus, just by looking at how these expressions you have here. If you have maybe do one example. So let's do comparing an of p of f. Still under the assumption that f is stuff. No like I get one. So then this should be the same thing as ap times an. Or I mean if p does not divide that. Because it's ecology, if you take the q to the nth coefficient, you will get this. And this would imply that on this side you have two possibilities. If p divide n or p does not divide n. If p does not, if p, let's do that if p does not divide n. If p does not divide n, you want to look at the nth square first. So some n sum in here. But this, whatever the exponent here must be divided by p. So you can only show some here. So this will tell you that p does not divide n. The left hand side is a p an. The right hand side is always this. Whereas if p does divide n, the left hand side now becomes a and p coming from the first term, and then p to the k minus 1 pi. in other words, you can, once you know, so this is for TP operator, you can also do the same thing for UP operator. Substitution the upshot is that once you know that, if you know that F is an eigenform, and you know all the Heckel operators, eigenvalues, then you already determine the Q space. So take eigenvalues. Determine the Q space. By this kind of recursive relations. So now let's talk a little. Just take a look. I'm already here, so I'm bound to talk to the alpha bits very quickly. Fine. I feel like, so I've thought a lot about, not a lot, I thought about this, why people define cell function this way. And at least I already thought that this is not such a reasonable thing to do. And I started to kind of, I personally feel that by reading some of marginally get some sense of literature. It's really how people define alpha without doing anything else. Right? Whenever some people have the tendency, whenever you have a sequence of things, just plug in things like this. I don't know. Maybe I understand it wrong. Okay. But of course, there's a better way to do this. So, let me explain why doing such a thing is difficult. I don't know, it's just very strange. Maybe I misunderstood some of the reason, right? So I consider the integration of f I1. So f is a function on f I. I integrate from 0 to I infinity along this line. Yeah, I should finish this. I'm really thinking of going up from here because you can evaluate I1. I'm integrating along. So let's do the calculation. And S is large enough. The real part of S is large enough. Let's you will see that it will help us with the first position. Okay, what do I have? Sum Q expansion. A and easily 2 pi I, okay, so 2 pi I times I y of y to s y. Now 2I becomes negative on me. Oh, excuse me, 2I, sorry, 2I n. So this exponent here becomes negative 2I n y. So now, convergence. So if y is large enough, e to negative 2 pi n y is very, very small. It's exponentially small. So whatever the polynomial growth is going to come everything. So very small. If y goes to 0, I took S to be large, the real part of S to be large enough, so this one will be very small. This will be roughly 1. So therefore, if I take the real part of S large enough, you should imagine that this sum and this integration altogether will be absolutely convergent. So I can switch them. Save some of this. I think this will save. Okay. Now I want to change the variables. So I want to change it to let's see, W being the one is minus 1. So W is 2I and 1. Now I have integration with sum. Integration of infinity of AN times now e to minus W. Now if I do W, then that's why y equals W over 2I n. The good thing of writing dy over y is that whenever you do this sort of scaling y, this will not change. So now I can take out the common factors. So AN over 2INS and S pi. Okay. Okay. Should be 2 pi n here. I check that out. Now I have e to the minus W times W in S. And now this is sort of this part is a technical function called gamma. So I can rewrite this. So that's your alpha. I'm not so sure. I mean, at least up to some point, I truly believe this is why people define alpha this way. But I'm not sure. I erased something I shouldn't have erased, but somehow the upshot is. So up to this point, I have to use the fact that my f is, I only use the fact that f is conform. I didn't use any sort of normalized eigenform, anything. But here's the exercise. Because we've talked about this relations about this Fourier coefficient an. If f is a normalized eigenform, then this sum we have over here have a better expression. It has a form of Euler product. I know most of you have some experience with the method Olympiad. This should be too difficult. Generating functions. Let's write it more explicitly. If P does not divide n, what you will see is this AP. At that price, so at good price I have this thing. At bad price I have this. So that's all I want to say about maybe just sort of people often write this as LP of F. That's to mean that, or same thing as here. To mean it's L factor at P. for L function, for general L function, it's a product of L factor at each of the prime. And of course, in the principle of all primes are equal, one should try to say what is this L infinity of Fs. And that is precisely the fact of the And the so-called functional equation is when you multiply all the sort of usual L function, namely the product of all the non-Archimedean L factors together with the Archimedean factor, the L function will have a simple functional equation. So that's an exercise. I've already posted that. Okay, so exercise. Functional equation for so-called complete L function. Prove that functional equation. Go back this equation and back up to Q. Basically, see what I have here is this L infinity part of this S. I'll talk about it. Wait. Good. But this course, after all, is mostly about arithmetic. So let's talk about the arithmetic part of the course. Let's first of all state a theorem, which hopefully, if I'm extremely lucky, I can prove it lucky. Actually, no. I should prove it next time. Or in some cases. Normalize taken. Oh man. Wait, K. So first of all, QF, meaning that Q, we're joining all the coefficients of F. I'll get right for that as summation of A and Q then. So it's meant to express it. QF, and this automatically will contain Q, all the coefficients of the Levin-Hammer character chi. Whatever this thing is, it's the number Q. Namely, it's a finite extension of Q. Okay, we'll prove this theorem in that case. Secondly, social Galois for every actually, next time we'll only prove this theorem for weight 2 on general not. For every prime lambda of there's an irreducible continuous representation. Yeah. Normalize. So for this discussion, you don't just need to be constant. Okay. So only this expression here needed to be normalized. Whenever you expand here, the first term goes at 1. That 1 is A1 over 1. Functional equation. Well, I mean, I didn't know. Maybe not so much. The scale goes up. No, I don't. on the other hand, something I want to convey is that, at least for myself, putting a sequence of numbers into this type of thing is not very reasonable to do. We only put reasonable things have expression close to. I guess for me, that what is an L function? L function, first of all, it has a form something like this. More importantly, it has an Euler product structure. That's something what I would call a L function. If it doesn't have an Euler product, I wouldn't call it L function. So therefore, that's why whenever I said this, I say start with F, normalize eigenform. But of course, indeed, in the construction, I really don't need F to be eigenform. Yeah. No, in fact, I don't need F to be eigenform. It's already there. It's always there. So I have for each normalized eigencosmorph F, I have an associated Galois called rho F of Gaussian Q, such that when P does not divide N or normal lambda, rho F is unbounded by P and the characteristic polynomial of the solution for each F. Whenever I write for these, I always use x squared minus 3ps. That's habit. Whenever I write this, when P is the coefficient here, and P is not in the level, rho is split at P of hard-type ways 0 and k minus 1. Oh, yeah. My bad. And the phi action on the decrease of this Galois rotation as characteristic polynomial x squared minus 8x. Maybe I should kind of give you some sort of slogan. Crystalline convenience is kind of equal to a. That's the way I memorize all these conditions. The noise that's very subtle. Often, even if you get the same result, it will happen that you may choose one mistake twice. I guess I can try to resolve. I need hold on a second. I need another situation. Mostly for p equals 1, but nonetheless, let's do it in general. So suppose that I have a prime p does not divide the coefficient here. But then this p would exactly divide, the m exactly divide that. And my chi of z and cross z is about p primitive. sometimes it's possible that. Oh, sorry. And when I write this, I mean I'm using one. Of course, Riemann NZ class will map to Riemann n over p class. P primitive means that it does not factor zero. So you cannot lower your lower the n by dividing by p. Then I can write my chi as chi p times chi away from p as the p of this character and away from p. Then I can ask what is scalar restriction Q. So my description only works when P is for P primitive. So this is unramified. Looks like so. Where? Unramified alpha is unramified character of Galactic Q. Sending radius of P to alpha. And chi p. Well, chi p we know that it's right. Chi p. We know that chi p is a character on Riemann p to the m p cross. So I can realize that the Galois array. So this will map to as a quotient of Galois group q p u theta p m over q. This is canonicalized for the Riemann p to the m cross. So in other words, if we're in the situation, that somehow p to the m exactly divided n, and this different type of character is p primitive, then this Galois is explicitly described as a direct sum of characters. First, one of them is unramified representation, whereas for v, the eigenvalue is precisely what it was. And because it's determinant, somehow I can determine that for v, the eigenvalue must be submitted multiplied to p to the k minus 1. Therefore, the other character, the unramified part, must be defined as well. And this Nibben-Tevez character chi will go into here as a ramified character. So this will back Galois group Q go to second coming extension. This is a more precise situation. No, I think we will use Legrand. Legrand will only use case when m equals 1. But it's important that somehow there's a replication. For our left Legrand. No. This questions about this? Let me make a remark. I didn't erase it because I want to talk about the alpha here. So for a Galois representation, rho from Galois Q to GLM, and if GLM QL bar equals GLB, such that for various values are algebraic. To be precise, I want to fix the isomorphism. Wait, we might do the following. Or maybe better way to assume a better problem. So I want to assume that a characteristic polynomial is convenient. Q condition. So that's just different. Then we can associate alpha at least when the real part of S is large enough by defining it to be L rho S. Let's see. First, find P not equal to L. I have the following factor. Many of you probably have seen a good factor, some good cases, but let me, 1 minus Rabinian of P times P to the negative S. This acts on, in general, not necessarily act on entire space, but this acts on the initial, the subspace of B that's fixed by initial subgroup. So that when you talk about Frobenius, this action is a well-defined matrix. It's a well-defined action. Of course, the definition of Frobenius is not unique. It's up to a conjugation. But then after conjugation, that's a factor. And also, you have to, I need a factor at P. Gives me factor at L. So this is if this rho is crystalline. Or I guess I need to understand the rho is Galois of L. This is the wrong in general. But let's just talk about the crystalline case. This is equal to 1 over determinant 1 minus crystalline for B L. Purple notation, but anyway. So, in general, it's not crystalline. You just take this D particularly semi-stable and then take the part that's fixed by S. Next, I want to say that the reason I didn't erase upstairs is because these two are equal. Another way to characterize the Galois if P does not divide N. You see that if P does not divide N, at least P not equal to L for N in L, is that we're in this situation here. The character polynomial of the Frobenius P is x squared, this thing in here. So therefore, if you take the determinant 1 minus Frobenius P minus S, what you will get is precisely this depth of x minus Frobenius P on B. Okay, if it does not divide NL, no invariance here. We know that the determinant of x minus Frobenius on B looks like that. So if I do 1 minus Frobenius P to the negative S, this will look like 1 minus A times P to the negative S plus the determinant of P A minus 1 pi P times P to the negative 2x. Remember the x is here, and then okay, I guess I can take this to be 1 and x. X then will become 1 and x squared. Now you're plugging x equals to p to the negative s, that's what you have here. So this factor is precisely the factor over there. And then you now divide as we just look at this example when p primitive. So this guy here is, because it has a very fast character, it has a certain character which is ramified. When I take inertial groups invariance, this part will be killed. So you only have the first part here. So that's why you have 1 minus AP times negative s. I just want to explain that somehow. This would statement that would statement of the associated galvanization. And you can also see this association of galvanization on level L function. For any reasonable L function, galvanization you can associate L function. And for any module form F, also associate L function. These two L functions will be the same if things are associated. And one more remark is that most of these are defined when the real part of S is greater than 0, very larger than, super larger than 0. Same here. But for Galois representation, if you associate an F function like so and an infinite product like so, it's not clear why such a function can be extended to the whole, have a meromorphic continuation to the whole complex plane. It's a very difficult task. However, for modular form, because we have the integration formula, because on the complete L function is some sort of integration of 0 infinity of f(i, y) of y to the s dy over y. Because it's such sort of integration formula, this gives us advantage of extending this to the whole, at least metamorphically, to the whole complex. So by looking at automorphic data, where Galois side you don't have any. So I guess somehow upshot. Upshot. LF usually it's always easier. To extend L function of Fs to the complex plane. S. And therefore, if we can prove rho F and F, they correspond in the way I just kind of described, this would imply that L rho F, L rho S, rho S, okay, at least meromorphically or good. I'll just stop here.